Okay, so now let's talk about continuous functions. This is actually more general than in complex. It shows up in many places of continuous functions. Okay, so first we have to define the limit. We say, limit of z going to z naught of f of z exists if the following is true. For every for all small numbers, epsilon, you can find a small delta number such that for all points close to z naught, the images, so let me call this L, the image f of z is close to this limit L. Okay, so let me draw a picture. It says here z naught. Draw a ball that skips the point, and this is a delta ball, and pick a point z. Then this point z gets mapped to a point within epsilon precision. So if you want to get epsilon precision, you've got to have delta pre-image. Okay, so this is epsilon precision, and it requires a delta to achieve it. Okay, so let's do a simple example, even though you won't really see this in this course, but still, for those of you who might do more academic things or research, this is very useful. Okay, so show show f of z equal to 2 times z is continuous at let's say z equal to a half. Okay, all right. So what does that mean? Suppose you want to be 1/100 close to the limit, which is 1, by the way. You can check. F of a half is 1. So to get this precision, what do we require? Well, let's see. So if you move around the 2, we require this as our delta, 1/200. So this is a half, and then you draw a ball 1/200. It will get mapped where is 1 here? It will get mapped to a ball 1/100. Okay. So you're 1/100 close. All right, but here I could have leave everything with epsilon, so you get that the delta is epsilon over 2. Okay, so the function has the limit. Let me define continuity. So continuous is when the limit as z equals to z naught is equal to the value at that point. And the motivation is what I wrote here. So we want, as z is really close to a half, we want it to be close to the image. Okay, but okay, this is not testable, of course. We will mostly just compute limits, like in calculus. Okay, so let's do some limits. So find the limit of z to the I, z squared plus 1 over z minus I. Okay, so hopefully you can see that you cannot just plug in I. So if you plug in I, you get a problem. You get over 0. So you don't want that. You get 0 over 0. And by the way, there is no L'Hopital. So please don't try to do L'Hopital rule. Okay. Right. So what you do is you simplify it. You factor. So we have z minus I, z plus I. They cancel out, and you just have 2i. But there is a version of L'Hopital that works. So L'Hopital for complex. So here it is. So if f and g are what we call analytic, and we will define this soon in the next clip, then you can do it. Then, if you have, z naught, if they're both equal to 0, then, when you take the ratio, you can take complex derivatives, which again, we will define in the next clip. But I think it's intuitive enough that we can do it here. So this limit is equal to 2z plus 0, and then over 1. And so indeed you get 2i. So, but please, you have to make sure that they're analytic, complex differential, which is slightly different than the usual differentiability. Okay. All right, so now let's do 2 non-examples. So consider the branch function. So it's just equal to z when it's not 0 and 1 otherwise. Find the limit as z equals to 0. Okay. Does it exist? Does it even exist? Okay, let's see. Right, so again, we want, well, first of all, what do we have? We have z, at 0, we see that it's 0, right? So we want this to be epsilon close. So we just set delta to be epsilon, right? So yeah, if you have z less than delta, then that gets mapped to less than epsilon. Okay, now here's the problem, but this function is not continuous, but f of 0 is 1, so f is not continuous at z equals 0, even though the limit f of z equals 0 is equal to 0, right? So you have this, you have the limit, but you don't have continuity. So limit and continuity are not the same. So please remember that. So we have the limit exists, okay? It exists, but it's not continuous. Of course, this is an artifact of the example, because what we usually do is, of course, if we're missing a value, we always define it as the limit. Of course, this is a contrived example. Because z at 0 will be defined as the limit. Okay, anyhow. So, okay, so you might say, yeah, so let me do another example to show this point. Consider the function f of z equal to sine z over z. Okay, so we have a problem, right? We don't know how to define it at 0. Okay, so we can use L'Hopital. So let's find how to define it. So this is indeed 0 over 0. We will show that these are complex differentiable. So by L'Hopital, this is cosine of z over 1. So this is just 1. So a continuous extension for f is the following. So sine z over z, and then equal to 1 when z is 0. So here we get continuity for free because that's how we defined it. That's how we defined the function. So we get continuity for free. Because we define this value to be this limit. Okay. All right, now let's do an example where we have neither continuity nor existence. Consider f of z equal to sine absolute value of z over z. will show that it has no limit at 0. Right. So has no limit as z equals to 0. Okay, let's see. So we have z to 0. Yeah, let me write the real and imaginary parts. So x plus iy, x plus iy. Okay. Now, as you've seen in calculus, so this limit has to work in any direction. So one direction is taking going along the real axis, right? So we set y equals 0. And if you complete this, you get 1. Okay. Now, we can also take this in a different direction. Take, take the limit along the imaginary axis. Okay. Now, because of the absolute value, we get sine y times 1 over y. And this is 1 as above times 1 over I, which is minus I, which is not 1. Okay, so so the limit doesn't exist because it has to be the same for all directions. The limit has to be the same from all directions, and so it doesn't exist. Okay, so we also get f of z equal to sine absolute value of z over z is not continuous. Okay, so that's it for continuity.